Hello, everyone. Thank you for joining me from wherever you're calling in. My name is Thomas Herbst. I am a volcanology student at the University of Missouri, and today we're going to be talking about the controls on volcanic eruptive behavior and the role crystals play in the explosive-effusive transition. To begin, we must ask what drives an eruption, and the answer is overpressure gas, and a magma's ability to release this gas controls its eruptive behavior. Its release is dependent on how the magma deforms. In other words, its rheology. So to set up the problem, I've made a compilation of published permeability-porosity data from natural, effusively, and explosively erupted products from nearly 40 volcanoes. Notice we have three distinct clusters of data. Low porosities are characterized exclusively by effusive data, while there's a heavy concentration of explosive products at high porosity permeabilities, with a transition zone in between where the data overlap. In this study, we propose an explanation of the following. If eruptions are driven by gas overpressure, which can be released through development of permeability, yet the least permeable magmas often erupt effusively, what mechanism can facilitate efficient outgassing at such low porosities? And why do explosive eruptions occur given their sample's high permeability? There lacks a comprehensive study on how crystal fraction affects permeability porosity, certainly so for crystal-rich magmas. And the controls on the eruption transition and its boundaries remain poorly constrained. By studying outgassing mechanisms as a function of crystallinity, we can determine what role crystals play in controlling this transition in silicic magmas. The goal of this project was to experimentally vesiculate hydrous dacitic melts with varying crystal contents. We then measured the subsequent bubble-driven inflation of the sample, shown here to scale, as a means of identifying the onset of permeable outgassing. In order to simulate decompression-driven vesiculation, our dacite samples were quenched at a final pressure of 68 MPa with 4.28% dissolved H2O to simulate a shallow reservoir. Once each sample was heated beyond its glass transition temperature, the melt was able to relax from its high-pressure configuration to atmospheric conditions, allowing degassing to occur. Instead of measuring uniaxial deformation or compression, we utilized our parallel plate viscometer to measure vertical expansion of the samples. This is the raw data from the parallel plate showing sample inflation with time. Each color and F number corresponds to crystal fraction in volume percent. To begin, we used the crystal-free sample F0 as a benchmark for vesiculation, undampened by crystals which vertically expanded about 40 to 50% of its minimum height. The bars on the right represent ranges of inflation for crystal-bearing samples normalized for the glass content, since of course melt and bubbles are changing volume, not the crystals themselves. In other words, these bars represent the expected range of inflation for each crystal content. And we can divide this plot into two segments. In the lower portion of the figure, we can see the crystal-rich analogs F70 and F80 saw little change in height due to bubble growth. As a result, their anticipated height change was overestimated. F60 was closer, but was overestimated as well. The point at which sample growth terminated is interpreted as the point when permeable outgassing was achieved. Samples were then quenched at this point, and although open system degassing might have continued, the termination of growth signals an efficient release of overpressure. Therefore, our samples preserved their porosity and pathway geometries that facilitated permeable outgassing. In order for this early stage outgassing to occur, bubble coalescence is likely not the primary outgassing mechanism given their high crystal contents. The answer instead is fractures. So what is the recipe required to fracture a magma? The onset of brittle behavior is dependent on the critical failure stress. With this in mind, tests by Cordonnier, Pistoni, and others showed that increasing crystal content does promote brittle behavior, and the addition of bubbles exacerbates this effect further. However, there is a crystallinity threshold above which bubble growth and connection are impeded. This promotes gas storage or bubble entrapment in more crystalline magmas. Consequently, the failure stress is increased if bubbles remain trapped within the crystal framework. Crystals, therefore, can aid or hinder gas escape, thereby playing a crucial role in controlling eruptive behavior. If we move to the upper portion of the inflation diagram, you'll notice F50, the 50% crystalline samples, far exceeded anticipated values by up to 26%, and in one case nearly overcame the crystal-free analog. Prior studies have stated, at least for crystal fractions less than 0.4, that the presence of crystals impede isolated spherical bubble growth and promote distortion. This in turn facilitates bubble coalescence and earlier outgassing. Coalescence, however, requires ease of ductile flow within the surrounding melt to occur. During inflation, degassing would increase local melt viscosity by creating a dehydrated halo, which further drives diffusion of volatiles, slowing viscous deformation. The overpressure provides the force exerted by an expanding bubble on the surrounding magma. And as we know, depending on the magma's crystal content and strain rate in response to this internal stress, brittle failure can and does occur in our samples at high crystal fractions greater than 0.6. And the reason is magmas become less compressible with increasing crystal fraction. Bubble expansion then leads to an increase in pressurization. SEM and tomography data show F80 was pervasively fractured and that samples preferentially preserved cracks within crystals, as we can see here. SEM data from F50 shows fractures in the melt are partially healed, implying that brittle and ductile deformation occurred contemporaneously above TG. This also further supports that crystal-rich domes are likely the healed remains of fractured, initially more hydrous magmas. SEM and tomography data were used to examine the microtextures in our samples to characterize the outgassing mechanism. As you can see in F50, bubble expansion led to viscous deformation, repositioning the crystal framework, while in F80, cracks propagate outwards from bubbly melt pockets, implying that fracturing was driven by bubble expansion. If sample inflation exceeded what was anticipated, as was the case in F50, then the degree of bubble entrapment must have increased, with neither ductile flow nor brittle failure being an efficient mechanism to release overpressure. This crystal framework, comprising 50% crystals, physically dampens bubble growth and impedes coalescence. At the same time, trapped bubbles increase the critical stress required for brittle failure. This prolongs outgassing. This demonstrates that permeability, in addition to bubble coalescence, can be achieved efficiently via pore pressure-induced cracking, and as such, we infer this to be the dominant outgassing mechanism in crystal-rich magmas. Now that we've identified the outgassing mechanisms in our analog experiments, the final piece is to relate our samples to the global data set I showed earlier. In this figure of permeability versus porosity, the labeled crosses are data from this study. Closed and open symbols represent effusive and explosive data for which crystallinity was known, respectively. And these have been binned by crystal content, each with a respective color. Each bin of crystal contents was fitted using the Kozeny-Kármán relationship, which calculates permeability as a function of porosity and percolation threshold. The percolation threshold is simply the minimum porosity that signals permeable outgassing can occur. Each percolation curve here, therefore, asymptotically approaches its percolation threshold. Our experiments also corroborate recent vesiculation studies in that increasing crystal fraction reduces percolation thresholds. We can also see this reflected in the natural explosive data, which sees a decrease from 0.7 for crystal poor samples to 0.25 for crystal-rich samples. However, previous studies have only tested vesiculated permeability for crystal fractions up to 0.4. Now, if we compare effusive versus explosive data for a single bin of crystal contents, we can easily observe that effusively erupted samples have lower porosities than their explosive counterparts. But we have yet to answer why explosive behavior occurs despite samples having high permeabilities. And we propose the key to explaining explosive potential lies not in the explosive data, but rather the percolation curves for effusive eruptions. Here we can clearly see there is a permeability threshold approximated by the curve for effusive lavas, at which outgassing proceeds rapidly enough that further permeability development terminates. In contrast, explosively erupted samples plot at lower permeability for a given porosity and were unable to reach the permeabilities necessary to outgas efficiently. We can now explain the controls on explosive effusive transitions and constrain its boundaries. Up to this point, this has not been possible without a comprehensive study testing the effects of higher crystal fractions on outgassing mechanisms. The transitional zone, which contains products of both eruption styles, is bounded by curves similar to the Kozeny-Kármán fits. This delineates a critical permeability above which magmas no longer pose explosive hazards. Magma can reach this permeability threshold either by a rapid increase in permeability due to fracturing or a decrease in porosity due to collapse of permeable pathways. Samples with high permeability and porosity can still erupt explosively because they fail to reach the very high permeability threshold for bubble-dominated systems. Our findings imply that this transition zone can be modulated by minor changes in crystallinity due to competing viscous and brittle behavior as magmas traverse this zone until it reaches a critical permeability. An intermediate crystal fractions about 0.5 characterizes those magmas most likely to alternate eruptive behavior. If we narrow the scope of eruption data, we can see our constraints hold true for historic eruptions like Mount St. Helens, which exhibited alternating behavior. I've also used eruptions from Mount Pelee here as an example to show its effusive and explosive data with respect to its permeability threshold. Of course, an ascending magma is a very dynamic system capable of adjusting its crystal content. And the point is that these interpretations emphasize the importance of characterizing the physical states of magma chambers, including their crystal contents and potential for gas storage. These interpretations can then provide a process-based framework for applying this information to eruptive hazard assessment. Thank you for your time, and I'd be happy to take any questions.